You lean into the throttle, the motor whines, and you accelerate smoothly up to exactly 15 miles per hour. Then the power cuts out. You hit an invisible wall, even though the throttle is still pinned to the max. Manufacturers use firmware to cap performance, artificially restricting the system, even though the battery and motor are physically capable of reaching much higher thresholds. Manufacturers deliberately throttle these machines before they leave the factory line. They do this to keep the scooter classified as low-speed electric bicycles under local traffic laws and to cap their own corporate liability. Riders bypass these limits using 5 distinct methods. The techniques start with basic physics and escalate all the way up to high-voltage electrical surgery. Accessing that dormant power requires the rider to intentionally discard the thermal and legal protections built into the hardware. The first method carries zero risk and requires no tools. When an electric scooter's tires are underinflated, they sag. This increases the surface area making contact with the asphalt, which generates rolling resistance and actively bleeds power away from the motor. This chart shows the direct relationship between tire pressure and battery efficiency. For every single PSI the tire drops below the recommended level, the scooter loses about 3% of its total range and sacrifices top-end speed. Inflating the tires exactly to the manufacturer's maximum rating eliminates that resistance. It is the necessary zero-risk baseline for getting the most speed out of the stock components. Many modern scooters use software to enforce speed caps. The electronic speed controller contains digital region codes that dictate exactly how much power the motor is allowed to draw, based on local laws. Riders bypass this by pairing their smartphone to the scooter via Bluetooth and using third-party utility apps to upload custom firmware. This diagram shows custom firmware overriding the system. It bypasses the default regional speed block and writes a new target threshold directly into the controller's memory, unlocking higher top speeds instantly. The motor now draws more power than it was programmed to handle. By writing over the factory parameters, the rider disables the thermal regulations designed to keep the system from overheating. Older or budget-tier models don't rely on software regions. Instead, they use a physical hardware loop to restrict the speed controller. A specific wire, often white or blue, runs out of the controller and loops directly back into it. As long as that circuit is closed, power delivery remains capped. The modification required to bypass this is purely mechanical. A rider cuts the wire to break the loop, then wraps both exposed ends heavily in electrical tape to prevent them from grounding out. Snapping that wire marks a clear point of no return. The rider has permanently altered the factory hardware, completely voiding the manufacturer warranty in exchange for a few extra miles per hour. Deep inside the controller sits a small metal component called a shunt resistor. The scooter uses it as a sensor to measure exactly how much current is flowing to the motor. This circuit schematic shows the controller reading the voltage drop across the shunt to enforce the factory current limit. Riders alter this by melting solder directly onto the shunt. Lowering resistance tricks the controller into pumping massive, unregulated amperage into the motor. More current means more heat. Pushing power past the specified limits initiates thermal runaway, melting the MOSFET power switches and permanently frying the circuit board. When a shunt modification pushes a stock controller to the point of catastrophic failure, the original hardware has to be ripped out and discarded entirely. In its place, the rider wires a high-capacity aftermarket controller. This requires splicing thick phase wires and perfectly matching the tiny cables from the motor's Hall sensors. This transplant replaces the factory logic with an unregulated, high-capacity system, effectively rebuilding the powertrain into something far more volatile than the original design. This chart compares an electric scooter's speed against its braking capability. While the speed increases on a linear path, the curve representing stopping distance shoots up exponentially. The stock brakes are simply not designed to halt that much momentum. The stress extends to the metal itself, subjecting a lightweight aluminum frame and small wheels, engineered specifically for 15 miles per hour, to the violent vibrations of 45 miles per hour rapidly accelerates material fatigue. Once a scooter exceeds regional speed and wattage limits, it legally ceases to be a bicycle. It becomes an unregistered motor vehicle being driven without plates, insurance, or a license. The factory limiters serve as a carefully calculated thermal and structural envelope. Breaking them strips away those protections, leaving the rider to shoulder the entirety of the physical and legal risk.